All right. So morning, everyone. Thank you for coming back to our course. It's halfway, the midway point. We're a little weary and tired and don't know what to do. And now have yet to learn a lot of stuff. Okay. So just grow a little patience and bear with me and see how far we can get. Okay. Now, we talked about shear design from last lecture. All right. And it was a little bit messy. We started with a simply supported beam sitting on a column. And then we also show you the shear diagram. And we pick the spots, right, at a critical surface, at the surface of the column support. And also we pick the half VVC, VVC, and etc. etc. So let me share the screen, okay? Let me share the screen, see what we have. All right, so this is what we have end up with from last lecture. Okay, so as you can see, we have a half span of a shear diagram, triangle shape, right? So we identify several things. First of all, let me use a little bit different color here, or maybe use this one. So we identify the max shear force at the middle span, not middle span, at the mid of the support, mid support. Okay, and so we identify the shear force at the face of the support, at a critical section, which is D away from the face of the support, and we also identify VBC, which is the total shear resistance, and also identify half VBC, half VBC. Okay, so these are the critical points. So far, you just have to remember these are the critical points on the shear diagram. Okay, we will decide how we are going to design the beam corresponding to these critical points. Okay, now the key message we give last lecture, we determine the distance away from the midspan of these critical points. They're corresponding for half VVCs, 1.5 feet, VVC, 3 feet, VU critical, 7 feet, and VU face, 9 feet, and VU max, 9.5. VU max, 9.5. Okay, so before we start, okay, this is just the shear diagram, right? And on the critical values. Before we start, right? So I mentioned that we're going to design it for different zones and etc. And let's just remove that for now. Let's just remove that for now, okay? Don't want to complicate things yet, okay? So let's take a look at the constraints first. Constraints, what are the limitations? What are limitations, right? So we have talked about there's gonna be a maximum shear resistance taken by the cross section. And there's also a maximum shear resistance that the web reinforcement can take. And they are correspondingly 4 lambda square root f prime c BWD and 5 lambda square root f prime c BWD. Okay, so I already calculated them out. Okay, so just to show you the equation, so this equal to 4 times 1, because it's normal weight concrete, square root inside the 4,000 psi. Okay, the width of the section, and mind you that the section, forgot to draw again here, has a BW of 12 inches. Okay, and depth of 24 inches. Depth of 24 inches. All right, that's just the section. Okay, so I have BW here 12 inches, depth of 24 inches, and I got this number to be 72.855, so 72.86 kips. Okay, save it effort. And I also want to check whether my section total applied shear will exceed the upper limit. Okay, upward limit. Remember in 318.14 we use a lambda, and the last lecture I said modification from 19 allowed only 5. So apply 5, and this is 5 multiply 1.0 multiply 4,000 inside, and 12-inch, 24-inch. And we got this number to be 91.07 kips. Just want to make sure, look at this number, 91.07. That is bigger than the maximum shear in this whole span, which is 85.5. So we're okay. So you will not run into the scenario that your section is not large enough. Your section is not large enough. Okay. All right. So now this is a shear diagram. This is shear diagram. Now I want to design it. Okay. So here's a quick question, right? Which shear force should I design for? Should I design for VU max? Okay. Should I design for VU face? Should I design for VU critical or VVC or half VVC? If I were to pick only one, I would have a problem. Why? Because say if I pick one, I say I pick the maximum one, right? That's the easiest to go. You know what? I'm just going to make sure the maximum section survived. So I provide all the stirrups in the spacing that satisfy the shear resistance of the maximum shear. Then my entire section will look like this. And I have this huge reserve that gonna go in waste. Not needed, but provided for additional cost. Why? Because we're lazy. Right? So that's not gonna work. That's not gonna work. Okay. So we say we want to be smart. We want to be smart. We don't want to do the maximum, right? How about we pick on the left-hand side, say, you know what, let me just pick this one value here. So if I pick VVC, say I just want a minimum shear, and then I have a huge portion of under design portion, which means these are dangers. These zones are dangerous, which is even worse, right? People got hurt if we have low design, right? If we have an inappropriate design. So what's the best way to do it? Right? So here is the strategy. Now, I copy the shear diagram. Here, down here, okay? And as you can see that I have a blue baseline, which is the shear diagram shown before. Okay? And I label all these critical points, half of VVC, VU critical, VU face, VU max. Okay? These are the critical points. Okay? So I want a design that, right? I want a design that will cover this diagram, okay? But will not be too excessive, okay? So I come up with these red lines. Okay? These red lines, all right? So let me just redraw them, right, to emphasize. So these red lines, right, come up with these red lines. What does it mean? What does it mean, right? It means I am going to pick VU max for this segment of design, okay? So the shear resistance and this red curves, right, this stepwise red curve is called shear resistance diagram. This is new term for you. This is called shear resistance diagram. You have the shear diagram, but yet you have a shear resistance diagram. Okay, that means I will design according to the red-shaped envelope that will enclose the blue shear diagram. All right, so first point I pick is VU max. Okay, and I traverse along this way to this point. Okay, and I will use VU critical as my second point. And I keep going till I reach the next point, which is VVC. Now, according to 14, at this point, I can perhaps go down a little bit and do another purple envelope like that to go back to VVC divided by half, because from 14, I don't have to provide any shear reinforcement if the concrete section is sufficient after divided by half, right? Divided by 2. Okay, but the new code 19 says you know what? That's dangerous. It's dangerous. Okay, you need to provide at least some shear reinforcement anyway. So I want to be clever. I will just design it for PVC. Better safe than sorry. Better safe than sorry. Right? So that is my new shear resistance diagram, and I'm going to design the shear for this. Okay, so looking back, what are the locations? What are the locations of these points, right? So I have 3 feet. I have 3 feet. Okay, for the first zone, I call it zone 1. Okay, I have 7 feet, right, to this point. So 4 feet of zone 2. I have 9.5 feet, that's the total, minus 7 at 2.5 feet for zone 3. Okay, this means I will end up, okay, if I draw the beam section, again, if I draw it, this means I will divide the beam at, remember this is half span. Okay? This is not entire span, this is only half span, okay? So if I draw this way, I would say now I can divide them in terms of segment. So now I have 3 feet distance away from here. And I call this zone 1, okay? And now next one is 7 feet, so 4 feet away from this end of it. I call it zone 2, right? Zone 2. All right, and the rest of it, and this is a little bit out of proportion, but this is actually 2.5 feet. So what I'm going to do is I'm going to shift this line here. Sorry, folks, made a mistake here. Let me redraw this, okay? This is out of proportion. Okay, the concept is the same, but just doesn't look right. Sorry about that. Okay. All right, so now I have 3 feet roughly. Let's put it here for zone 1. 3 feet, zone 1, and 4 feet of zone 2, and 2.5 feet of zone 3. Okay, and now when I put stirrups in it, this is side view, by the way. When I put stirrups to it, in zone 3, I have a very dense packing. Okay, so this will have a spacing of S3. And zone 2, I have a little bit less spacing, something like that. Okay, and this will be another spacing S2. And for zone 1, I will have minimum. Okay, minimum. All right. So with this, essentially, I will just have 3 segment design. I will only need to design 3 spacings, right? 3 spacings. And how are they designed for, right? So we will design S1. Based on what? Based on phi VC. Based on phi VC. And you can get this number, right? Phi VC equal to phi 2 lambda squared F prime C BWD. And you can calculate out, and phi equal to 0.75, right? So you can calculate out. So design S2 based on what? Pick out a critical number, right? Remember here, based on, this is 1, this is 2, so based on this one here, VU critical, right? And what's the number of that? I think that's right down here, 63, so 63 kips. Okay, and S3 based on what? Based on phi VU max, which is, what is the number? Come on, 85.5, 85.5 kips. Okay, so now you have a beam that have 3 segments, and each segment have a different shear spacing, and each shear spacing shall be designed by these critical values. Now, how I got these critical values? I obtained them from shear diagram and corresponding shear resistance. Okay. So this choice 3 segment is the design I choose, Now, of course, you can choose more sophisticated design, okay? You can choose more sophisticated design. For instance, I'm going to use this color. So for instance, you can do this every step, right? Every step. You can do this every step. Now you have more precision, right? And you have saved more materials, supposedly. But remember, when you have more segments, it's gonna increase your construction cost, right? Imagine how the field engineer will curse your name when they see this design, because they have to design 4 different zones and ask their field technicians put them down 4 different spacings. That's quite costly. It's quite costly. All right. So for the sake of labor cost, which is quite expensive, and time and materials, right? When you have to put spacers and those are extra costs, try to simplify your design enough, right? Try to minimize more of spacing, yet provide sufficient. So you ask, what's the balance point, Bob? Which one should I pick? So 3 segment is the best I experienced so far that I can pick. Now, 2 or 3 are the best. If you go beyond the 3, 4 or 5, that seems a little excessive because engineer have to design segment. But when you have a large span section, we're talking about 20 feet, 30 feet, yes, it's necessary to go farther than that. Okay, all right, so this is the shared design concept. Now, we haven't finished yet. This is just show you how to design it, isn't it? But you can simply do this following an example we did last lecture, well, 2 lectures ago, right? On Monday, right? If not on Monday, last Thursday, right? So my next quiz to you is quiz 7 is calculate calculate as 1, as 2, and as 3. Follow previous section calculation examples. Okay? This is quiz 7. Okay? All right? Okay. Any questions on this, guys? It's quite important stuff, okay? So any questions on this? Are we getting this? Are we okay with this? Anything, folks? Are we good?
I have a question.
Yes, sir.
What are we solving? What example are we solving S1, S2, and S3 for?
Yeah, so remember we did a shear design some time back,
Oh,
right? Remember it? So sorry, this should be the 15. Is it 15? I think there was an example, right? Is it 14 or 15 I did? Yes. Oh, my lecture sequence is a little bit messed up. Oh, sorry about that. Okay. Anyway, so do you see this?
yeah, I see it.
Right. So how we did last time is we pick a VU, right? We give different numbers, right? And we were to find different spacings, isn't it? Right?
Okay.
So we're going to do the same thing. But now the difference is we only have 3 numbers. We only have 3 numbers. Okay. So let me go to 16. We have this number as VU.
Yeah.
So we can think about this way. And this number as VU2 and this number as VU3. Is it better? Clear?
Bob,
Yes, sir.
do you want us to assume number 3 stirrups for our
Yeah. Oh,
AV?
okay. Sorry about that. So I forgot. Either number 3 or number 5.
So you
Okay.
want us just to pick which one and just state which one we chose?
Yes. Yes. Pick one and you go all the way, right? Okay. All right. So my personal favorite for small beams like this is number 3. But some people like it to be stiffer, so they have larger spacings. I want to caution you a little bit because you want to make sure spacing is at least minimum, right? There's a minimum as, remember? Okay, so if you pick number 5 a lot, you realize that sometimes you don't have to do any calculations, lazy side of it, but you still have to make sure they exceed the required value. Okay, Any questions, guys? Is it clear how to do this? Do we need more information for this? Okay. All right. So let's do the tomorrow, Thursday. I will circle back a little bit, see how we do on this quiz, because tomorrow I will leave the share homework. All right. So please try a little bit at least to look back on the previous example. Look back on the previous example. I believe it's lecture 15. Lecture 15. Yeah, right here, lecture 15. Okay, I have two lecture 15. I'll sort it out. Okay, I probably go lecture 15.1, lecture 15.2, or something like that. But please go over this previous lecture notes. This shows you all the detail how we design for it. All you have to do is pick the three numbers now with this newer numbers, right? And find your three different spacings. Okay. All right. Any other questions on this? It's quite important. Any other question on this? Are we good? All right, I don't hear anything, so I think we're okay. But again, on Thursday, we'll come back and talk about this a little bit more, okay? All right, so just want to give you a try, all right? Just want to give you a try. Now, we are done with share almost, okay? So done with share. Okay, you can expect homework tomorrow. You can expect homework tomorrow. I'll design it today. And we're going to go into one-way slab. One-way slab, okay? So lecture 16, part of it, so like one-way slab. One-way slab. Okay, one-way slab. All right, so what is one-way slab? First of all, what is one-way slab? Okay, now let's take a look. Let's take a look. We define a large, okay, we define a large, flat, oh, sorry, let me see here, that large, flat plate, supported by beams, walls. Let me just increase it so you can see better. Walls, okay, structure, okay, and steel beams, etc. It's just a big giant plate on support, right? Big giant plate on support. Okay, so that's a slab. That's a slab. All right. Now, the key word of this thing is one way. Key word of this thing is one way, right? What does it mean by one way? One way, right? So one-way slab is a slab that bends primarily along one direction. Okay, so let me just add that. One-way slab, just being lazy here. One-way slab bends along one direction. Okay, in another word, you only have to calculate moment in this direction, right? And the other thing, I'm gonna put important signal mark here, is that it's a unit strip. It's a unit strip. Okay, what does unit mean? It's usually by 1 foot. Okay, 1 foot. So put it into a picture, put it into the picture. So that means I have a flat slab like this, okay? And only it bends in this direction, only it bends in this direction, like so. Okay, like so, only it bends in this direction, like so. And it sits on the support, it sits on the support right here, like so. Okay, along the whole thing, okay? You need a support. All right, so with the support, it bends only in one direction. And even further, let's define it, right? I will define this direction along the bending direction to be L1, that's the bending direction. And I define the other direction to be L2. Okay, So one way means it bends along L1. Right? So some other geometries we have to remember that the slab height or the slab thickness is HF. Okay, and when we design it, we said it's going to be a unit strip. We said it's going to be a unit strip. What does it mean, right? Unit strip means it goes this way. This is a cross section, means every time we design it, we design the moment capacity per 1 foot, or 12 inches. 12 inches. Okay, 12 inches. All right. So when we have, okay, definition of one-way slab, when we have L2 over L1, and be careful, okay, L2 over L1, right? The transverse direction over longitudinal direction is bigger than 2, and that is one-way slab. One-way slab, okay? Meaning that it bends in the shortest direction, okay? All right, okay, so this is a simplified view, all right? In the reality, when you see a one-way slab, it does not simply sit on the support like this. They will sit on the beams, or sit on the column, and all kind of things, right? For example, I'll take a look at top view of a one-way slab. So the top view looks like this. So this is a bay, okay? This is the bay, okay? You can think this is the beam, and I have another beam going this way. This is top view, by the way, okay? So top view. I have another beam going this way, and these will act as my support. Okay. Now, on top of that, I also have beam, and then it's going this way. Okay. Dashed line meaning these short beams, okay? These short beams are sitting on top of it, okay? And I also have beams going this, sorry, oops. Okay. This is the beam on the edge. Okay. I also have beam goes on the side here. Okay. Here. Okay. And I have a columns here. This is the column. This is column. Okay, so I can call this bay A, bay B, and I call this bay 1, bay 2. All right, and if I have smaller internal beams, I could draw there, but right now this is the situation. This is what it looks like. Okay, this is what it looks like. So I will have to tell you that. I'll have to tell you what is the one-way direction. Okay, but these seems like AB and 1, 2, they're almost the same length, right? So I'll add small beams. I'll add small beams in the middle to shorten it. And why is that? Because now with this, I have span length from this beam to center of this beam right here. Okay, this is called L1. All right, and I have distance here, and this is called L2. Okay, L2. All right, so now once I satisfy the condition L2 over L1 is bigger than 2.0, I can call this one-way slab. All right, so this is the one-way direction. So what are we designing for? We're designing a strip. So let me use shaded area red. Okay, we're designing a strip, which is the slab, unit slab we're designing for. And this is 1 foot. Okay, so that is the design. Okay. Now, if this is not simple enough for you, and you can think of it, so this is basically the support. This is basically support. Okay, and this is the other end of it, and this is the strip we're designing for. And if I cut a cross section here, what should I see? If I cut a cross section here, what should I see? I see a nice strip that has a width of 12 inches and have a height of HF. Okay, and this needs a tension reinforcement at the bottom because they always see positive bending in the middle. Okay, and that is the unit strip we're designing for. Okay, I need you to have this visual understanding. So is this clear to you guys? Any questions on this? Anything confusing about this part? Do we know what we're designing for, guys? Okay, seems to be straightforward, so pretty quiet. Okay, all right, that's fine. So this is what we are designing for essentially. Okay, essentially. All right, so now that's the basic concept, right? By basic concept, but we need to provide what, right? We need to provide what? So typically the height of the slab or the thickness of the slab typically is given. So typically provided. You know it. Why? Because there are so many constraints. I need to satisfy the height of the slab. So if, for example, it's a parking garage, I cannot afford to have a height that's so big, so it will cut into my capacity. So say this typically provided. Okay, so the 1 foot unit strip is already given, right? You know you're designing for unit strip. So the section geometry is given. So the main thing for the design of one-way slab is to design for reinforcement. Design for reinforcement. Okay, so that's all we care about for one-way slab right now. It's reinforcement design. So I'm just going to write down here reinforcement design, right? We're only caring about designing for reinforcement. Okay, but there are 2 types of reinforcement. 2 types of reinforcement. Okay, so one type is so-called flexure reinforcement. So flexure reinforcement. Naturally, this take cares of MN. Take cares of MN. Okay, and the other reinforcement is for shrinkage and temperature. Shrinkage and temperature. You say,
Hey,
Bob.
Bob.
Yeah.
I
Jinx.
have a question.
Go ahead. Right.
So how do you account for like shear resistance in these slabs? Because I don't like stirrups don't make sense to me because it's so wide.
That's a good question. So you see, HF is normally very stocky. It's very short. Okay, and the slab usually does not take a whole lot of shear.
Okay, gotcha.
Right. So we don't usually provide any shear reinforcement to the slab.
Okay.
We
Makes sense.
try in a structure design, we try to allocate those shear to the beams underneath it.
Gotcha.
Right, right. Can you see it, right? So it is the column and the beam usually from the slab beam slab column system. It's the columns and beams take care of the shear. The slab you should just take care of the bending, right?
I
You gotta
gotcha.
think, yeah, you gotta think about the purpose of slab is to have something that your car runs on, isn't it? So they're not the critical structure component. They're more like take care of the deflection, so you won't sag too much.
Gotcha. Thank you.
Right. Yeah, sure, no problem. Okay, thanks. So now the other type of reinforcement is temperature shrinkage. Temperature shrinkage. Okay, so why temperature shrinkage is important? Because I have very thin slab. My concrete cover is very small. Okay, and also because I have a large plate, it's continuous. It's continuous, it's long. So when temperature heats up, it expands quite a bit, right? Quite a bit. So I have cracks generated due to the thermal expansion. Why? Because the concrete won't expand and it shrinks and there's support constraining them, so it will generate stress in the concrete and it will crack. Okay, so you need to provide reinforcement to relieve those stresses. So we need to design reinforcement for temperature and also shrinkage. For temperature, also shrinkage. Okay, but there are also other considerations we can get into it. But these are the two major design consideration. So that's all the reinforcement we design for. Let's take in the first one, right? Flexure reinforcement. Flexure reinforcement. Okay. All right. So naturally, flexure reinforcement, what do we need, right? We need bending moment mu. Okay. And we need to come up a phi mn. Okay. And we need to provide the steel, right, for bending. Okay. But now be careful. All these on the slab is per unit length. In other words, per foot. Per foot. So when we're given a moment to slab, so moment, apply moment for slab is oftentimes kip feet per foot. Kip feet per foot. Be careful, okay? We will have this in the second exam and people will make mistakes. It is kip foot per foot. Now kip foot is a unit for moment, right? But don't forget it's per unit length, per strip that we're designing for. Per strip we're designing for. Okay, so why this is critical? Because in the spacing, remember we have to put the bars, we have to put bars, okay? And that area of steel is not a single bar, 2 bars, 3 bars that we always see in sections. It is actually area per foot, So when you calculate the area of steel AS, okay, per foot, okay, this is the required steel, okay, that is equal to the bar, right, the area of bar you provided multiplied by the spacing, or 12 inch the per foot unit divided by the spacing. Okay, this is bar spacing. Okay, and this is area of bars. I know this is still very hard to fathom, but let me show you, okay, with a diagram. All right, and this you can find out in ACI code 6.5.1. Okay, so what is this? Is when I see the cross section of the slab, right? And I normally provide bars here. Like this is cross section, and this is AB, 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 and I have a spacing in between. This is S. Okay, but when I design it, right, I need to convert this into a strip. Right? So this is 1 foot. Right? It could be here, or it could be here. It could be anywhere, isn't it? Could be anywhere, right? So I have to change this, convert into an idealized section. So this idealized section will have only 1 foot of distance. And we'll have an imaginary bar, and this is AS. Of course, it's per foot. All right, so how to do the conversion, right? I got to satisfy A bar, right? A bar, use black looks better. A bar divided by S, okay? Because this essentially, you can think of it as steel provided per spacing, per distance, okay? This has to equal on the right-hand side, this AS per foot divided by 12 inches. Okay, so this is also steel, imaginary steel provided per spacing. Okay, so you do the cross, right? You do the cross, and this returns this equation. That's how it comes from. I mean, that's where it comes from. Okay, so in another word, when you provide a bar to a slab, you got to do the conversion, right? You say, I provide, for example, number 9 bars. This is number 9. I'm just making things up, okay? And I say, all right, I have a distance between the bars, say, for example, 12 inches. That's too ideal, right? 10, make it 10 inches. Okay, so what would be the AS provided for the slab, right? So how to do that? You do a calculation like this. You use this equation here. So you say AS per foot that equal to AB, which is 9 bars, so 1 inch squared. Number 9, so 1 inch squared. Okay, and this is AB. Multiply 12 inches divided by 10 inches. So you got about 1.2 inch squared per foot. Okay, so that is to say, if you give the slab number 9 bars and let them space of 10 inches, then you have a provided steel per foot of actually 1.2 inch square per foot. Okay, don't forget, there's a conversion. Okay, there's a conversion. Why this is so important? Because we're going to need this to calculate the moment capacity. Okay, we're going to need AS per foot. Okay, this to calculate the moment capacity. Okay, all right. I think this is a good point to stop. I'll update our notes. And sorry about the messy situation about 15. I will clear it up. And you'll see the lecture recorded on YouTube as well. All right. So let me stop here. Any questions? Folks, any questions on this? This is kind of important, right? Because you need this for the exam. I will assure you in the exam, problem number 1 will be a slab. Problem number 2 is going to be shear, right? Think of it, right? It's that obvious, right? When we have a problem in irregular section, you know, that's probably it. Probably it, okay? So any questions for me on this? Anything? Are we good? Wow, pretty quiet. Okay, okay. Well, this is the concept. So next lecture, I will start calling more questions, have more interactions on Thursday. So thank you for attending today. Let's stop here and I see you on Thursday. And of course, you're welcome to stay behind if you have any questions and you need to talk to me and we can talk a little bit. All right, thanks and see you tomorrow.